So here's example 3 of our resolving forces topic. And here's the situation. So a particle of mass 5 kilograms, so here's our weight 5g, is held in equilibrium. So this important word, meaning that all the resultant force is going to be 0, by 2 light inextensible strings. So here's our strings, so the tension's going to be constant, T1 and T2, because they're 2 separate strings, at angles 15 and 20 to the horizontal. So this thing is being sort of held in midair by these 2 strings. And it's being held in equilibrium, so there's no resultant force happening. The thing's being held static in equilibrium. Find the tensions in each string. So we're asked to find T1 and T2. So let's have a look at resolving some of these forces, and we're going to look, as normal, at vertically. And we'll take up as positive, and then we'll look at horizontally, and again I'm going to take right as positive as normal. So if we look at these 2 forces, T1 first of all, over here, let's split this up into its perpendicular components. So we're going to have a component horizontally and a component vertically, and the resultant of those 2 is going to be this T1. So as we've seen before, this one, if I look at the right angle triangle, this side is adjacent. Our force overall is always going to be our hypotenuse. So this is going to be T1 cos 15. And then this is going to be T1 sine 15. And then on the T2 side, same idea, horizontally and vertically, looking at the components there. And the resultant of those 2 component forces would be this resultant force. So again, here we're going to have T2 cos 20, because it's adjacent to the angle, and T2 sine 20. So now that I've done that, and my advice is always to put these things on your diagrams, because here's your working now all done really, here's your method all done. Now let's pull it together and look at vertically and horizontally. So vertically, taking up as positive, I've got T1 sine 15. I've also got up as positive T2 sine 20. And then in the opposite direction, pulling downwards, I've got my weight 5g. So there's my resultant force, and that must be equal to 0 because the whole thing's being held in equilibrium. Okay, so there's my equation 1. I've got 2 unknowns in this I'm trying to find. So let's have a look at finding a second equation. So let's go horizontally, tell the examiner that I'm taking right as positive. So horizontally, to the right as positive, T2 cos 20 is tending to pull the particle in this direction and then pulling the particle in the opposite direction. So minus T1 cos 15 degrees. And again here, the overall resultant force is 0 because it's being held in equilibrium. So nothing's happening horizontally, nothing's happening as a resultant force vertically. So these 2 things are equal to 0. And now we've got 2 simultaneous equations, and they're not particularly nice simultaneous equations, but they're okay. You know, maybe in this one, I don't know, take T1 cos 15 over, make T2 the subject, sub that back into here, rearrange the whole thing and find T1. I'm going to leave you to do that, so I'm going to do my usual sort of ... I want you to have a go of that, make one of the tensions the subject of one, sub it into the other, solve, and then sub in to find the second tension, and you should overall eventually, so please do this, get, I think I'm just looking at my solutions here, 80.3 newtons to 3 SF for T1 and 82.5 newtons, I think, to 3 SF for T2. So have a look at this, fill in these steps here, a little bit of playing around with rearranging these to find T1 and T2. That's question 3. So our last example now, example 4, one where we're not given a diagram and we're asked to look at what's happening here. So let's read through this. A box of mass 2 kilograms rests on a smooth horizontal force. So because it's smooth, that means there's no friction holding this thing back. So if it doesn't tell us there's any resistance, then nothing's going to be pulling this box back. a force of 3 newtons is applied at an angle of 30 degrees to the horizontal, and it causes the box to accelerate horizontally along the floor. So what's going to happen here, and I'll draw a diagram in a second, we're going to have our box on the floor, which we're going to treat as a particle. We're going to have this force at 30 degrees pulling that way, and this is not going to lift off the ground, it's going to move, accelerate horizontally along the ground. So this, pulling this way, is going to pull it this way. And imagine, I don't know, something like a lead on a pet or something like that. You know, if you're pulling this way, we're not putting enough upward force to lift this off the ground, we're just giving enough force to move the thing along the horizontal ground there. Okay, let's draw a quick diagram then. So horizontal floor, smooth, we've got our box here. It's 2 kilograms, so I've got 2G acting downwards. Force of 3 newtons applied at 30 degrees. So there's my 3 newtons, and it's telling me that that is acting at 30 degrees to the horizontal. And we're asked to find the acceleration of this and the normal reaction between the box and the floor. So let's put some of these forces on then. We haven't got any friction acting backwards this time because it's a smooth horizontal floor, so there's no resistance to this motion once it gets going. We have got a reaction though because this box is resting on the floor here, so we've got this reaction force, we've seen that before, acting perpendicular to the ground. And so that's what's happening here. So let's have a look at finding the acceleration. So finding the acceleration is certainly going to be to do with resultant force equals mass times acceleration. So let's have a look here. We're going to, again, look at vertically and horizontally. It's the horizontal aspect that's going to give us the acceleration, and then the vertical aspect will get the normal reaction involved. Okay. So let's look at this, splitting my 3 newtons then up into its vertical and its horizontal component. This one's adjacent, so this is going to be 3 cos 30 degrees. And this one is going to be 3 sine 30 degrees. So I'm replacing my 3 newtons with these 2 equivalent components. And then let's have a look, as usual, at our vertical and horizontal. So vertically, up as positive. What's happening? I've got that reaction force plus that vertical component, 3 sine 30 degrees acting upwards, and then acting downwards, I've got my 2G, and that resultant force is equal to 0 because in the vertical direction, nothing's happening. It's only moving horizontally along the floor. So in the horizontal direction, there is a resultant force, but in the vertical direction, there isn't a resultant force. So that's going to be equal to 0. Okay, so we'll leave that for a sec. Let's go back to horizontally. And again, tell the examiner I'm taking right as positive here. So here, what's happening? Well, here, my resultant force now is not going to be equal to 0. My resultant force is going to be 3 cos 30 degrees, and there's nothing else happening horizontally here. So that's what's happening here. So what's that going to be? That's going to be mass times acceleration. So this mass times acceleration, my mass is 2, so 2a is going to be 3 cos 30 degrees. I'm just going to move that up slightly, I hope you can see that. So there's my 2 equations, and actually now I can answer these questions really quite easily. So from this one, my reaction force is going to be, 2G minus 3 sine 30 degrees. So 2G minus 3 sine 30, and that's going to give me 18.1 newtons. And then horizontally, I've got my acceleration is 3 cos 30 over 2. So 3 cos 30 over 2, 3 root 3 over 4. So that's going to give me 1.29903. So 1.30 meters per second squared to 3SF. So that's our 4th example of resolving forces completed. And I'd like you now to do some practice on this. So have a look at today's task for the questions I'd like you to do.